Hello friends, welcome to Control System Lectures. I am Dr. Nitisha Shrivastava. In this lecture, we will start with the stability analysis of control systems and deal with Routh Hurwitz criterion. So, a linear time invariant system is stable if the following two notions of system stability are satisfied. That is, when a system is excited by a bounded input, the output is bounded. This is one notion, and the next one is, in the absence of input, the output tends towards 0, that is the equilibrium state of the system, irrespective of the initial conditions, and this stability concept is known as asymptotic stability. This notion is related to the presence of input, and this notion is related to the absence of input. What is absolute stability and what is relative stability? Absolute stability refers to the condition whether the system is stable or unstable. So, it is a decision whether it is a yes or no. But what about relative stability? Relative stability is actually a quantitative measure, and once the system is found to be stable, it is to decide how much stable, how stable it is, and this degree of stability is a measure of relative stability. So, relative stability is a quantitative measure about the variation of parameters, how much a parameter could be varied so that the system remains in the stable region. That is how fast the transients die out in the system. Now, this graph depicts about the root locations on the left half of the S plane. As the root move farther away from the imaginary axis on the left half of the S plane, then we can see that the transients die out more quickly than to the location of roots which are more towards the imaginary axis. So, as the roots are farther away from the imaginary axis, then the transients die out quickly and the steady state is achieved much faster than for those roots which are nearer to the j omega axis. This is the response curve of a second order system when subjected to unit step input. Now, this is about the impulse response for the location of the roots. Since we are talking about stability of a system is related to the location of the roots. Now, here if the location of the root is on the left half of the S plane, then the system is stable and reaches the steady state value, and if the location of the root is on the right half of the S plane, then the system is unstable. Similarly, if the location of the two pair, that is the pair of conjugate roots or complex conjugate roots are on the left half of the S plane, then the transients die out and the system is stable. However, if the roots lie on the right half of the S plane, then the system is unstable, as clearly seen with the impulse response of a system which is having roots on the right half of the S plane. And if the roots are on the imaginary axis, then there are sustained oscillations, and remember that is always two roots, that is there is a pair of root having positive and negative values, and if there are double pair of roots, then the system is unstable. Similarly, there is a single root on the imaginary on the 0, that is on the origin, then the system is stable, whereas if there is double root on the origin, then the system is unstable. So, as we had seen the analysis of a second order system, it is easy to find the roots of a second order system, and thus the location of the roots results in the stability. and once the roots have been determined, we can look at the location of the roots and decide whether the system is stable or unstable or marginally stable. If the roots are lying on the j omega axis, we say that the system is marginally stable or marginally unstable. It means that here it is comfortable to find the roots of a second order system, but not all control systems are second order systems. The system could be higher than the second, and in that case of finding the roots is difficult. Now, to decide how much the system is stable or whether the system is stable or not for a higher order system, there is one criterion, that is the Routh Hurwitz criterion. Routh Hurwitz criterion is applied or is an algebraic method that provides information on the absolute stability of a system. So, through this criterion we get to know whether the system is stable or not, and that has characteristic equation with constant coefficients. So, it is required that the coefficients of the s to the power terms have a constant value. This criterion tests whether any of the roots of the characteristic equation lie in the right half of the S plane. As has been said that Routh Hurwitz criterion is used to know whether any roots are lying on the right half of the S plane, and the number of roots that lie on the j omega axis and in the right half of the S plane can also be found out through this criterion. However, the point which is related to this is, though we get to know how many roots are located on the j omega axis or on the right half of the S plane, but it is not possible to determine the values of those roots. So, Routh Hurwitz criterion help us to determine whether the system is stable or not and how many roots lie on the right half of the S plane or on the j omega axis. If the roots lie on the right half of the S plane, then we term the system to be unstable. So, this is the necessary but not sufficient condition for Routh Hurwitz criterion. The Routh Hurwitz criterion says all the coefficients of the equation have the same sign, and this is applied to the characteristic equation. How is the characteristic equation obtained? We obtain the closed loop transfer function, and the denominator of the closed loop transfer function is known as the characteristic equation. This characteristic equation is set to 0 to identify the roots, and none of the coefficient vanishes. To be precise, none of the coefficients are 0. For example, we have s cube plus s square plus 2 plus s plus 2 equal to 0. The coefficient here is 3, the coefficient here is 2, the coefficient here is 8 and 2. So, it means that the coefficients are constant, that is all coefficients of the equation have the same sign and constant values, and none of the coefficient vanishes, that is there is no coefficient with a 0 value. Why we term this as not a it is a necessary but not sufficient condition, because it is also possible that even if there are non-zero constant terms, coefficients having non-zero value and of the same sign may not have all roots that lie on the left half of the S plane. So, this is just a basic condition, that is the necessary condition to go ahead with the Routh Hurwitz criterion, that all the coefficients must have the same sign and no terms should have a 0 coefficient. So, this is the necessary condition and not the sufficient condition. So, what are the steps involved in determination of stability? For example, let us consider the characteristic equation which is having s raised to n term, s raised to minus n with these coefficients and a naught. Now, what is the first step? The first step is to arrange the coefficients of the characteristic equation into two rows. Once you get the characteristic equation, and what is characteristic equation? I repeat that we obtain the closed loop transfer function of a system, and the denominator of the closed loop transfer function, that is the poles of a closed loop transfer function, are the roots of the characteristic equation. So, the first step is to arrange the quantities in 1 and 2 rows in first and the second row. Now, here let us say that it is a n. So, a n is in the first row, whereas the term a n minus 2 will be the second term, a n minus 4 will be the third, and as so on. Whereas, the second row will consist of the next term, that is the next coefficient a n minus 1, and then skip this n minus 3, skip n minus 5, and so on. Thus, the second row is formed, all counting from the highest order term. So, the highest order term will be written here, and then correspondingly we arrange the first and the second rows. This is the first step. Then the second step is to form the array, that is the Routh's array, or known as the Routh tabulation. The first and the second row are arranged, then the table is continued with the help of the numbers what we obtain from these already written coefficients. For example, let us take the characteristic equation which is having order here is 6, order of the characteristic equation is 6, and therefore, now we are writing this s raised to 6 here, s raised to 5. This is in the decreasing order, this is just for reference. This left half part is just for reference. Here you can see that the highest order coefficient is a6, a6 is written here, the next term is a4, this a4 and a2. Then we do not have terms here, we have a naught, next is a naught. So, these are arranged with the highest order coefficients. This is a 6th order transfer function, sorry 6th order characteristic equation. So, s raised to 6, that is a6. This part is only for reference. This is the Routh's tabulation. This is a5. Then what remains with us? This a5, a3, a1, and we do not have a term. So, we write it as 0, a5, a3, a1 and no term. So, we can write a 0 or just leave blank. It is the meaning that the coefficient there is 0, we do not have anything after that. Then after arranging the terms in the first and the second row, then we find the value of this first element here in the third row. First element in the third row is obtained by, we can see, a5 multiplied by a4 minus a6 multiplied by a3 divided by this quantity a5. This is the first element of the third row. Second element of the third row is obtained by a5 multiplied by a2 minus a6 multiplied by a1 divided by a5. Here we can see that the quantity a5 a2 minus a6 a1 upon a5, this is b. And then how is this product obtained? This is a5 multiplied by a naught minus a6 multiplied by 0 divided by a5. So, this quantity is nothing but a naught, because a6 into 0 is a 0 value, and this is 0, it can be left blank or kept as it is. Similarly, how is the first element of the fourth row obtained? It is a into a3, a into a3 multiplied by a5 into b, this value, divided by a, this quantity, and correspondingly the next term a5 into A2, that is this B multiplied by, here we get it as A into A2 and A into A1, okay, A into A1 minus A5 into A0 divided by A. This element is obtained, and here we obtain the element A multiplied by 0 into A5 multiplied by 0 upon A, we get it as 0. Thus, the table is complete till we obtain the element. This is for reference what would be the last row. So, last row is for s raised to 0. This is how the Routh's tabulation or the Routh's array is framed. First, the first step is to arrange the coefficients in the first row, and then starting with the highest order term, and then arranging the second row, and later arranging the remaining elements of the Routh's table or Routh's array. What is the conclusion from the Routh's tabulation? So, once this table has been obtained from the characteristic equation coefficients, then what are we inferring from, what are we concluding from the Routh's tabulation? So, here now the first step in determining or concluding what is the stability of the system, it is to be checked the first elements of all the rows. The first element of all the rows are checked, and if there is no sign change, if there is no sign change here, this is the first element A6, A5, capital A, C, E, F and A0. The first element of each row is checked, and if all the elements have the same sign, that is there is no sign change. When there is no sign change and all the signs, not necessary to all the signs to be, I mean it is necessary that there should not be any sign changes here, then it is termed as the system is stable. Now, if there is a sign change from one element of the row to the next element of the row, then the system is unstable. And how many roots, that means the system is unstable, means that there are roots lying in the right half of the S plane. When the roots are lying on the right half of the S plane, it means that the system is unstable. And how many sign changes occur, that many roots lie in the right half of the S plane. So, just read out this. If all the elements of the first column of the Routh's tabulation are of the same sign, it means the roots of the characteristic equation are all in the left half of the S plane. This means that the system is stable, and the number of changes of signs of the first column equals the number of roots in the right half S plane. So, as I told you, as many changes of sign, for example, we get C as minus C and then E as a positive value, that means there are two sign changes. Sign has changed from positive to negative and from negative to positive. So, there are two sign changes, and it means that there are two roots in the right half of the S plane. This criteria, that is the Routh Hurwitz criterion, answers the question whether a system is stable or not in a yes or no form. That is, looking at the elements of the first elements of all the rows, we decide whether the system is stable or not without the need of actually determining the roots of the characteristic equation. Otherwise, how do we determine? We look at the location of the roots on the right half or the left half of the S plane and decide whether the system is stable or unstable, and if the roots lying on the imaginary axis, we term it as marginally stable or marginally unstable. However, in this method we do not however, in this method we do not determine the roots of the characteristic equation. We simply find out whether the system is stable or not without actually knowing the values. So, this criterion gives only the number of roots in the right half of the S plane. We also know how many roots are lying, and but no information on the values of the roots is obtained. Let us take one example here. We have a characteristic equation s raised to 4 plus s cube plus 8s square plus 16s plus 5. Now, arranging the table in this form, the first step is to write the first and the second row, and it is written like this. The coefficient of s raised to 4 is 1, this term is over. Next is 18, the term written here. Next is 5, the term written here 5. What remains? We have 8, so 8 is written here, 16 is written here. We do not have term after this, so we can write it as 0. So, according to this tabulation, A5 into A4 minus A6 into A3 divided by A5. Thus, we obtain the next element of this row, that is 8 into 18 minus 1 into 16 divided by 8. This minus this value divided by 8 is 16. Then 8 into 5 into 1 into 0 divided by 8, we get it as 5. Now, 16 into 16 minus 8 into 5 upon 16, we get it as 135, and then we do not have any term here. So, this becomes 0, this also becomes 0 basically, or we can leave it blank, and this is obtained as 135 into 5 minus 0 upon 135, that is 5. So, this is how we complete the table, that is the Routh's array, and find that there are no sign changes. There are no sign changes in the first column. The first element of each row, that is the first column, are all positive, and hence the system is stable. Let us take up another example, that is the example 2. The characteristic equation here is of a fourth order function. Now, here we can see 2s raised to 4 plus s cube plus 3s square plus 5s plus 10. So, arranging the first row, this is 2, 3, this is 3, and then we have this 10, 10 is placed here. What remains? 1 coefficient of s cube and then coefficient of s. The remaining terms are 0. Obtaining the first element, it is 1 into 3, 1 into 3 minus 5 into 2, 5 into 2 divided by 1. The value comes out to be minus 7, and when the value is minus 7 here, there is a change of sign from the row previous to this, that is the second row and the third row, there is change of sign in the first element. There is change of sign in the first element, that means the system is unstable. Let us see what are the other values. It is 1 into 10 minus 2 into 0 divided by 1, it is 10. Similarly, 7 into, it is minus 7 into 5 minus 10 into 1 divided by minus 7. Yeah. So, this value comes out to be 45 by 7. So, here we get it as minus 7 into 5 minus 1 into 10 upon. So, this is a positive sign here, we get it as minus 45 upon minus 7. So, there is a positive sign, from the sign is changing from minus to from plus to minus and then minus to plus. You see 7 into 5, 735 minus 10, 45 by 5. Okay. So, there are two sign changes here, and we can see that this term is again 10 minus this by, so we get the value 10 here, it is a positive value. Therefore, we can see that the sign has changed from positive to negative and from negative to positive. So, there are two sign changes in the first column, and the equation has two roots in the right half of the S plane. So, stability through checking the sign changes in the first column decides whether the system is stable or not, and this is related to Routh Hurwitz criterion. And this means that the system is unstable, and since there are two sign changes, that means there are two roots that lie in the right half of the S plane, and the two changes is decided from positive to negative and negative to positive. Thank you.